So hello everyone, this is lecture 30 for the mathematical physics. In the last lecture we ended our differential equations, and from today onwards we will start the complex analysis. So let's see first the introduction part. Means first we will introduce you with the syllabus, what we will cover in this complex analysis. So this will be complex numbers first. In it we will study about complex plane, addition, multiplication, subtraction, division, complex conjugate numbers. Then we will see polar form of complex numbers, multiplication, division, integer power, roots of complex numbers, then De Moivre's formula. Then we will see analytic functions, complex functions, limit means in analytic functions we will have complex functions, limit, continuity and derivatives. Then we will see Cauchy-Riemann equations and Laplace equations. Then exponential function, trigonometric functions. These are some special functions. In the complex plane we will see hyperbolic functions and logarithmic. Then Cauchy's integral formula. Cauchy's integral formula, it was means it was special formula something. Okay. So Taylor and Laurent expansion. Then we will see zeros and singularities of function, residue theorem, and some definite integrals. Okay. So this will be your syllabus which we will cover in the complex analysis. So let's start with the introduction part, that is complex numbers. So first of all let me introduce that there was many equations was there, but then the mathematician came to this thing when they have this x square equal to minus 1. Then they have to thought about it that what solution is possible for this. Then we introduce this complex number, means you can have this kind of equation also, and if you try to solve with the formula, quadratic formula, minus b plus minus root b square minus 4ac divided by 2a, then you will get something like this, and this will be negative. So they were stuck at this, that how to solve this kind of problems. So that's where we introduces the complex number z. So by definition, a complex number z is an ordered pair xy, written as z equal to xy. So this is a complex number which can be represented in the form of z, that is xy. This is ordered pair where x is real and y is imaginary. Okay, imaginary of z, and xy is not equal to yx. Here if we write 0 1, then this is called the imaginary unit, and this is actually I. Okay, remember this is I, and I equal to 0 1 in the form of ordered pair. So remember this was the iota we defined in the form of ordered pair. Now two complex numbers are equal if their real parts and imaginary parts are equal. So when we will say them equal, when their imaginary and real parts are equal. So real x will be represented by this form x0, okay, imaginary part 0 1. Now let's introduce two algebraic operators, that is addition and the multiplication. So addition of two complex numbers is directly possible. Just add the x terms and the y terms, you will get the resultant addition of the complex number. And remember this formula for multiplication, this is very important. For x z1 z2, you want to multiply z1 and z2, that is x1 y1 x2 y2. So it will be x1 x2 minus y1 y2 comma x1 y2 plus x2 y1. So remember this. Now let's see, if we want to multiply two real numbers, that will be can be written in the form of complex as x1 0 x2 0. So both are real, x1 and x2. So if you put this formula here, x1 x2, it will give you x1 x2 minus y1 y2, that will be 0. And then again x1 y2, x1 x2 means sorry x1 y2, so 0, and x2 y1 x2 y1, so this will again 0. So you will get x1 x2 this. So this was the multiplication. This was just an addition, it was simple, x1 plus x2 0 0, but here it was multiplication of this. So we get this x1 x2 minus 0 0 plus 0. So it will be again x1 x2 0. So two real numbers can be multiplied directly and you will get this. So this formula is valid. Now let's see how we get this z equal to x plus yy. So by definition, this is a real number x0, it can be represented as x0 x, and we represented iota 0 means this was our iota. So if we write 0y as iota y, means it can be written as this. How? Because iota is 0 1 and y is real, so y0. Okay, so this is the multiplication of I and y, so we can write iota is 0 1, we already defined it, and y is y0. Now if you multiply these with this formula, you will get 0y. Okay, so now the addition of these two will be xy, that will be x0 and 0y, and this is our iota y and this is our x, so we'll get z equal to x plus iota y. So that's how we came to this number, that is our complex number z, which can be written in the form of x plus iy. Okay, by definition. So that's how we get this. Now we can find these I square. I square is nothing but I dot I, and we defined iota as 0 1, so it will be multiplication of 0 1 0 1. So use this formula, you will get this 0 minus 1. So the product of I will be real minus 1. Okay, and that's how we get I square equal to minus 1. Iota is under root minus 1. Now we can define these two operators also, that is subtraction and division. These are just inverse operation of addition and multiplication. See, we can write subtraction in form of addition, you know that, and division in form of multiplication. See how? The difference is z equal to z1 minus z2 is a complex number z, such that we can write z1 equal to z plus z2. So it's just a sum of z plus z2. So that's how you can represent subtraction in form of addition. So if we have z1 minus z2, so that will be x1 minus x2 plus iota y1 minus y2. Remember this. So in the form of quotient, if we talk about division, then z1 is divided by z2 will give us z as quotient. So z1 can be written as z into z2. So this will be our form for the division form of multiplication. So where z2 should not be equal to 0 is a complex number z, such that z1 equal to z multiplied z2. So remember this. So let's see how we divide a complex number with other complex number. So x1 plus iota y1 divided by x2 plus iota y2. So just to rationalize this, we will introduce these terms later, the conjugate and all. This lecture is just an introductory lecture. So it will be x2 minus iota y2, x2 minus iota y2. So this will give you a square minus b square because of a plus b and a minus b. So x2 square minus iota y2 square and iota square will give you minus again. So you will get x2 square plus y2 square. And multiplying this, you will get this. Separate the iota terms and the real terms. So this is your division. And remember this formula, it will be fast or easy to calculate this division. Otherwise you will always multiply these kind of terms. So this will be our z equal to x plus iota y. It means if you call this whole term as x, whole term is y, so this division will be x plus iota y. Now let's talk about the complex plane. So as in the real system we have Cartesian coordinates x, y. So same we can represent one of this axis as imaginary axis and the other axis as real axis. Then this plane is called the complex plane, and we can represent any complex number in this plane. Okay, by this x plus iota y, means just real part will be here, imaginary part will be here, and you can locate any complex point in this. Okay, just like x plus y, so this will be x, this should be y, so this point is representing this point, z equal to x plus iota y. Now how we can add two complex number in this complex plane? See, if this is z1 and this is z2, then draw the parallel lines and use the parallelogram law. So this point will represent the addition of this z1 and z2. Okay, so these are not vectors, but you can use that parallelogram law to add these two complex numbers here. Okay, because here also we are having the number divided in the two axes, that's why you can use the vector formula here, but these are not vectors, remember this. Now we can find subtraction of two complex number in the complex plane also, as we already defined that if we want to find the z1 minus z2, then we have to see z1 equal to z plus z2. So just it is a very easy thing, means you need to find z1 minus z2, then you have to add z1 with minus z2. So minus z2 will be in this form here, so use the parallelogram law. So this vector this vector represents the z1 minus z2. Okay, now there are conjugate numbers. So what are conjugate in complex? So if z is equal to x plus iota y, then z conjugate will be just I will turn into minus I. So this will be your conjugate number. Z conjugate will be x minus iota y. Okay. So how you can represent this inside a complex plane? So see, just reflection of a point along the x-axis will give you the conjugate number, because here x will remain same and this term will change. So this is our reflected, means reflection is called the conjugate, okay, along the x-axis. So that's how you can represent this conjugate in a complex plane. And remember this z into z conjugate, if you multiply these two numbers you will get a plus b a minus b. So a square x square minus I square y square, so I square will give you minus, so x square plus y square will be z bar. So this is this. And if you find the mod z is nothing but length of this, and it is equal to under root x square plus y square. So that's how you can represent mod z square as z bar, and mod z will be under root z bar. That's how you come to this relation. Remember this relation, very important. Here this x is nothing but, if you want to find this x value, this will be addition of z plus z conjugate divided by 2, because this will cancel out and it will give you x again. So that's how you can find. Means if you try to solve this equation and find the value of x and y, so you will get these. X will be this, y will be this. Just try to solve these equations and find the value of xy. You will get these as your xy, and you can directly verify from here also. Z minus z bar means this minus this will give you 2 iota y divided by 2, so you will get y. Okay, so that's how you can verify. Now let's see some of the properties of complex numbers. So z1 plus z2 conjugate will be z1 conjugate plus z2 conjugate. z1 minus z2 conjugate will be z1 conjugate minus z2 conjugate. z1 z2 means it is the product here, so it will be equal to z1 conjugate multiply z2 conjugate, and z1 divided by z2 conjugate will be equal to z1 conjugate divided by z2 conjugate. So take the values z1 z2 as 4 plus 3 iota, 2 plus 5 iota, and try to verify all these properties. They will all satisfy these properties. Okay, means you can take the product of z1 z2 and then take the conjugate, and otherwise you can first conjugate this, then conjugate this, and then take the product. You will get the same result from this property. So try to verify. Let's see one more property, that is z1 plus z2 mod square plus z1 minus z2 mod square should be equal to 2z1 square plus 2z2 square. So how you can check this, or you can derive this also. So how? Let's see first z1 plus z2 whole square. So consider this whole as a complex number. So we already defined this property. This square will be equal to z conjugate. So this is z and this is z conjugate, so we can write this as this. Now this conjugate will be divided on this here by using this property. Now you can directly multiply them. So it will be z1 z1 bar plus z1 z2 bar plus z2 z1 bar and z2 z2 bar. So this will be our mod z square, mod z1 square. We can write it as it is, and it will be mod z2 square plus z1 z2 bar plus z2 z1 bar. Same you can expand this also, z1 minus z2 square mod ka square. Okay, so you can write it in this form, just same as we defined this. Writing the conjugate and this whole term, you will multiply and you will get this. Now we will add these two equations, then you will get this equation again. So that's how you can verify this result. Now how to find mode of a complex number. So if you need to find the mode of this equation or this complex number, first you need to rationalize this. So you will just multiply 1 plus 2 iota, 1 plus 2 iota, and you will get a result in this form. Now mod is nothing but under root x square plus y square, so it will be 1 plus 4, it will give you under root 5. So mod in a complex plane represent the length of that point from the origin. Okay, so that's it for today. This was an introductory lecture. Okay, so see it again. These terms will be very helpful in the future lectures. So thank you everyone.